No, we could do it doesn't listen very much. It's way after 30 seconds.
So good. I felt so good.
It says hit pound, but you hit no expect.
All right, everyone. We're going to talk about what we do when we make a model, and it's not perfect, which is every model, right? But we want to do something useful with it. And usually we have some ecological question, but the type of question that we're asking is really going to determine what comes next, right? And whether some model that we've developed is good enough. And the main takeaway I want you to take from this lecture this morning is basically that your model can be pretty bad and still be really useful for the types of ecological questions that we're asking.
Really?
Really.
All right.
Yeah.
Awesome.
Okay. So in my lab, we playfully say that it's time for science once we develop the model, because now we actually get to go like learn something about the world. So we're like, okay, I did my homework, I trained my model, now I get to do science. And so today we're going to do science. So it really starts with what kind of questions you're going to ask. And throughout the lecture, as I talk about different things that you might do with your model, or ways that you might think about whether the model is good enough, and how to like validate some of the outputs, it always is going to come back to these questions. So some of the like high-level questions that we often are asking in ecology are: can we detect some rare event? Can we measure some form of biodiversity? At which locations or at which pieces of my system is some focal species present, right? Or also how many, sometimes we want to know how many of something that we're interested in there are, or how much of it. Is the population changing over time? A different question, right? So change over time requires a different data type. What are the temporal patterns of some behavior? We're on maybe a shorter time scale. And then a little bit more complicated, sometimes we're interested in how some external factor is affecting something that we're studying, the presence or the abundance or the behavior of some species we're interested in. So these types of questions each are going to require that we do something different with our model. And thinking about like our model in terms of precision and recall, or the metrics we've talked about, you can imagine that can we detect a rare thing as a very different requirement for precision and recall than how does some external factor affect the presence of our species, right? So there are scenarios where we need really high recall, and we need to know like every time that something was around that we actually captured it. But there are also scenarios where low recall is fine, and really what we care about is just detecting something at some point, and we don't necessarily need to detect every single one. So the use call is going to determine where we are on our precision recall curve, or where we put a threshold, right? If we're using a threshold to create detections and non-detections. So I'm going to show a lot more histograms today. I showed histograms last time I talked. And just as a reminder, I like to generally plot the histograms with the logit score, so the raw output of your model, rather than the model crushed into the 0-1 range. You can plot them either way, but that's what's on the x-axis here, right? It's just the score. And we're just counting in a bunch of little score bins how many scores fell into that bin, right? And we can color them by, if we know the labels, we can color them by the positives and the negatives. So the absences and the presences. And so when we put a threshold down on here somewhere, right? We can put a threshold somewhere where we're going to have like 99, 100% precision, which just means like none of that orange histogram gets to the right. So everything that falls to the right of this threshold or this score is going to be a detection, right? And so if we're in a scenario where we want to say like, I don't really want to manually validate all of my results, but I also don't want false positives. Maybe this model is good enough that I can choose a threshold where I have very high precision and I have some sort of mediocre recall, right? Now my recall, how many of the fraction of blue clips that I've detected is maybe like half. And depending on the application, that might be good enough or it might not be good enough, right? But you can see that in this model, in this set of scores, or this histogram, there's no threshold we could choose where we both get super high precision and super high recall, right? So it's just that trade-off. And we can alternatively decide, for instance, that we wanted to be somewhere that has really high recall. But notice that if we, in this particular set of scores, so our model wasn't really good enough to completely separate those two histograms. And if we require like 99% recall, if we want to capture all those blue clips, then we're also capturing like the majority of the negatives. So in this case, the model that was really good for if we need high precision but don't care about recall, actually is not very good if we need really high recall, right? Does that make sense? Like this isn't a very useful model if we need high recall because we're not even throwing out that many of the non-detections. So the other thing that comes into play when we're choosing a threshold, if we need a threshold in our scores and create predictions, is what is the cost of expert review? Like, is it okay if I need to review literally like 1 million samples from my data set of 100 million? Or do I need to filter my data set of 100 million samples down to 5,000 clips that I can review in a single day or something? And in my experience, the number that your experts or your team or you should be willing to review is actually higher than you might just expect out of the box. Because maybe out of the box you're thinking like, okay, I'm going to go review 10 samples and I'm already going to know the answer. Or my CNN is going to be so good that I don't need to review anymore. And sometimes that happens. But the other thing that can happen is that your model is okay, right? The model has some overlap. And the best thing to do with a model like that might not be to keep working on the model, but to just commit to the fact that, okay, I'm going to have to review like 10,000 samples. And when you actually compute the amount of time it's going to take to do that, it's much less time than it would take to invest in developing a better model, or even finding better training data and retraining your model sometimes. And there are other advantages to this, right? Because in some systems, like, it's just never going to be acceptable to assume that the outputs or detections of your model are correct detections of some biological event without actually going and verifying them. And if you're in a scenario like that, there comes a point in your pipeline where you just have to sit down and do manual verification, or have your collaborators or experts do manual verification. And I'll just note that also, like, this process of manual verification can be like boring, but people tend to be much more willing and excited to do it when your model is turning up something exciting, right? So if you told someone like, take 10,000 random clips from this like years worth of camera trap data or years worth of audio recordings and review them, like that's a really boring task. But if you say like, take the 10,000 most interesting detections that my CNN created out of these like set of 10 rare species you never see, and the user is like finding this rare thing, then that's actually like an exciting review task. And I just throw up one comment from a collaborator in my lab who was very excited that like this ruffed grouse detector was detecting this rare event in the audio. And he was listening to a random selection of the detections out of this model and finding the thing that if he had been randomly listening to audio, he wouldn't have found, right? And the kind of secret here is that this model could have had very low recall. And yet those like most confident detections were actually the thing we were looking for. And so, yeah, just kind of like trying to make the point that like sometimes it's okay to sit down and do a lot of manual verification. That's not a failure of your machine learning.
So in this example with Japan, which clips did you show?
So this is like a detector. It's actually not a machine learning detector. It's a signal processing detector, but it just creates detection, non-detection for this event. And so he randomly listened to a subset of the detections that it created on our audio.
I see. So you didn't even do like a precision recall trade-off confidence thresholding.
No,
okay.
No. We have like precision and recall in some validation set, but this is like, okay, I took the model, I applied it to new field data, And let's just see if some of those detections are actually the thing. Wow, it's actually the grouse, like this rare event.
Okay, so you just gave like all detections of grouse, you gave them
Yes.
to P. Okay.
Okay, so something that's really important to think about when we decide to like use a model on our system or across a variety of sites is that often we'll have a picture of like what the histograms of the absent and present samples might look like across the entire kind of like data set, right? And so this is kind of a best case scenario because even if you've taken a random sample of the actual field data where you want to do your study, which is the way that you'll know this histogram is like representative of your data, not of just some other data set, right? It still shows you this aggregate over all of the camera traps or all of the audio recorders or all of the different sensors in different locations, right? And at any one particular location, the question is, does the histogram of positive and negative or absent and present clips actually look the same? That's really important, right? Because if the histograms look different, then the same threshold for one location or a different threshold means a completely different thing. Does that make sense? So I'll just give a couple examples. So like sometimes you'll go to a site and you'll just have like a few labeled samples of that site, but you can tell, or at least it looks so far like the samples from that site are generally falling into the same distribution of that overall site. But then you'll get to another site and it'll actually have a completely different distribution, right? So this is like from the same larger set as this original distribution, but at this particular set, there's a lot of very low scoring clips and there's no positives. So it's a completely different distribution of scores. And this is an audio data set. So the question is then like why? Like why is there this complete different distribution? Usually it has to do with some sort of like shift in the contents or domain. So in this case, the regular site on the bottom that kind of mirrors the overall pattern has a bunch of birds in it. And this is kind of a typical spectrogram. Eventually you find one of the focal species, and when it doesn't have the focal species, it just has some other species going on. And then this site that just had very low scores is just completely silent. Why it's completely silent, I don't know. Maybe the recorder failed. Maybe it's recording at night instead of during the day or something. Or maybe that's just like dead zone and somehow there's no noise there. But it's just kind of something to be aware of, that just because you have the histogram or a precision recall curve or a precision recall at a specific threshold, even measured at the specific site where you're doing your research, it doesn't mean that you can trust that same relationship will hold for each of the study locations. And this becomes important when in ecology we want to ask questions like, how does something vary across sites? Or how do the covariates at one site predict this thing that I'm measuring? So I'll talk a little bit about how we can overcome this like obstacle or this challenge. Okay. Yeah, and in the second half of this lecture, we're just going to go through like a few examples of like, here's a real system and a real challenge and a real model, and the question we wanted to ask and like, what do we actually do with the data? But first, I also just want to talk about what is the worst model that's still useful. So this is kind of what I said at the beginning, like sometimes you can have a really bad model that depending on the question you want to ask is still useful. And the reason it's useful is because you care about one specific thing and you're willing to accept losses in some other way, right? And so this is just a set of 6 different models for 6 different bird species, which is predicting the presence of the bird in an audio clip. And this is kind of like a real life scenario. Like sometimes we train a model and this is the performance we get. And you might be thinking like, wow, it's really bad. And in a way it is, right? Like your metrics that you would look at compared to some machine learning paper on this data would be really bad. If you look here, you can't really get up to like 80% recall until you have like 40 or 50% precision, right? You're not really throwing away a lot of the negatives if you want to keep a lot of the positives. But the other aspect of this we can look at is what is happening out on the very right side of the histogram. So all we care about is detecting eastern whippoorwill, or sorry, that's eastern wood pewee, or if all we care is detecting the veery, and we don't care about detecting every single one, then all we need to see is that the highest scoring clips or samples where the thing is actually there are scoring higher than the highest scoring clips where it's not there, right? Because then we can go in and review some clips at this very highest scoring region, and confirm the presence. So in the case where you don't care about recall, any model where the highest scores are at least sometimes the target class is a good enough model. Does that make sense in the context of the histograms I was showing?
What if those high scores are just in one location and not another, though? Like, what if, or something like that, right? I mean,
Yeah.
then would you fall down at some places and not others? Like,
yeah, we'll kind of show this in a case study later. But basically, what you want to see is that the highest scores on whatever stratification you're interested in are the thing that you're looking for. And interestingly, the actual score doesn't matter as much as the fact that it's the highest score at that site.
okay.
Right. So so this is an example of like a really bad model where it might still be really useful if all we need to do is detect something is there or not, because we can go out to these highest scoring clips, and if we listen to a few of them, we're going to detect the thing we're looking for. On the other hand, if you need high recall, what's the worst model that's useful? Any model that throws away a large fraction of your data, right, while retaining the thing that you're interested in. So this is kind of often this is the scenario with like the onboard detection on a camera trap, or the types of sensors that are throwing out a lot of data and only retaining some. As long as the thing is throwing out most of the data and retaining the thing that you're interested in, then it's a useful model, right? So going back to this model is actually not useful at all if you need high recall. I wrote the wrong word here. If you need high recall, you need to capture all these orange ones, and in the process, you're going to capture all the blue ones. So in some sense, a model that needs high recall has like a higher demand of performance than a model that needs high precision. There's a lot of things we might do in ecology that kind of come like after the detection step, right? So these are things like occupancy modeling, abundance modeling, counting individuals, time series data. And I'm not going to go into this because that's like an entire course or many courses worth of information. But I just highlight a couple things from those types of models that are important in deciding whether you need high precision or high recall, or what you should be watching out for in your model's performance. So how many people are familiar with occupancy models? Some, but not all. Okay, so I'm just going to give like a very high level intuition for what an occupancy model does. So the idea of an occupancy model is you just want to know, I have 10 or 20 sites in my study system, 100 sites. I want to know which of them my focal species is present at. And we're assuming that if the focal species is present at that site, it's just present at that site all the time. So maybe you detect it or you don't detect it when you go, but like for the entire season that you're studying, the focal species is just present or not present. That's the closure assumption in an occupancy model. And so if you do a series of visits at each of your sites, you either detect or you don't detect the species. And that's the only information that goes into an occupancy model, is a series of detections or non-detections at each of your sites. So maybe you go to 3 sites and you detect it 3 times in a row at site A, 3 times in a row at site B, and none at site C. So intuitively, if we had to guess how many sites are occupied here, we would say 2, right? These 2 sites are occupied because I detected it, and this one is not occupied, I never saw it, right? But you can imagine that a slightly different scenario where, oh boy. Okay. So we went 3 times, we only detected it once at site A and once at site B. But we're assuming that if a species is present at a site, it's just always present. So we mark both of these sites as occupied, right? And we also notice that even when a site is occupied, we only detect it on average like once in 3 times that we go. So now the question is site C occupied? Well, maybe it's not occupied because we didn't see it, but maybe since we only see it on average 1 out of 3 times, it's occupied and we just missed it. So the idea of an occupancy model is statistically to do exactly what we just did logically there, which is fill in some of these gaps where we didn't see something that may have been just because of imperfect detection rather than because the site was not occupied. So that's kind of the high-level intuition of what an occupancy model is doing. And there are a couple things that we can translate into the world of like machine learning from this. So occupancy models account for imperfect detection, which means that you don't care about recall being close to 1. They're specifically designed for scenarios where recall is far from 1, and the more visits you have, the more you can have low recall, and the occupancy model will deal with it. But occupancy models are very sensitive to false positives. So you don't want to have false positive detections in your occupancy model, or it will basically screw up all of the estimates it's making. That means our precision has to be close to 1. Occupancy models can learn covariates for occupancy, which means they're trying to learn something about where your positives occur based on some other data you collected, right? So you go study a bunch of birds and you take habitat measurements, or you go study a bunch of fish and you also measure the temperature and depth, right? How do you predict where the species is occupied based on some covariates? And in addition to covariates for occupancy, you can also measure covariates for detection. So that's how do we measure how likely it is that we missed something even though it was there, right? So, maybe your detection of your fish is worse when the water is cloudy, right? And so you can actually use the information that the water was cloudy to predict the fact that you might have missed something that was there. So those are called covariates for detection. Right, and then repeated surveys. So repeated surveys are difficult for like traditional human observer methods because you have to keep going back to a site and repeating the survey, and it takes like linear effort, right? 10 surveys takes 10 times as much effort. And the nice thing about a lot of remote sensing applications is that we kind of get repeated surveys for free. We leave the sensor there for the whole season, and every day we can consider a survey. So we have this power of a high number of repeated surveys. And I'll just put a red flag here on the precision equals 1 because that's the part we're going to have to watch out for when we use our machine learning models for an occupancy modeling context. Okay, something very closely related to occupancy models is habitat suitability models. So a habitat suitability model is basically you run an occupancy model with a bunch of covariates to learn the relationship between some variables you measured and whether your focal species, the thing you're interested in, is present, right? And then you just map that onto a larger area where you haven't measured the thing you're looking for, but you know the covariates. So maybe you have like satellite imagery and you know kind of the habitat types across the entire US, but you've only monitored your species at a few locations. So then you learn those covariates that have predicted whether your species is occupied or not and predict on a larger map. And so I'll just raise one more red flag here, which kind of applies both to occupancy modeling and habitat suitability models, which is that remember that you can model your detection probability, right? So you can have predictors on whether you detect a species or not. But if that detection probability changes across your locations in a way that you haven't accounted for with your covariates, the term would be unmodeled heterogeneity in detection probability. It's basically going to screw everything up, right? Because if you don't realize that some sites are like cloudy water and some sites are clear, then you're going to wrongly predict how many sites were actually occupied because you're not accounting for that difference in the ability to detect the species at those sites.
So just on the topic of covariates, we discussed first detections, individual detections in a trace, in a subtrace. Then we discussed the spatial distribution. Do you have any thoughts on the temporal distribution? I have noticed that some birds are extremely particular about the time when they show up. And if you don't look for them at the right time, you simply don't see them.
Definitely,
And
yeah.
maybe correlates also between different species. If one shows up at 7, the second one will show up at 8, I don't know. So
Yeah, time can absolutely be a detection covariate. And it typically is in a model for birds or species that are definitely changing their behavior or detectability in time. So time could be like date, but it could also be time of day. And both of those are almost always going to be detection covariates in a model where you're, for instance, trying to predict occupancy of a breeding bird on the landscape.
And to build up on that, have you any thoughts? So the biggest covariate I found for people like us is human activities. And is there a literature on using these sensors to detect automobiles, people talking, chainsaws, guns, and whatnot?
Yeah, there absolutely is. In acoustics, a lot of people were doing those types of detection before they were even doing biology. And so, yeah, there's specific models sometimes for like chainsaws, gunshots, and then even just doing like a human voice detection can be really effective for detecting human activity. And those could become covariates for detection. Yeah, I can maybe send out some papers on that type of monitoring. Great, thanks. Okay, we're not going to spend too much more time on statistical models because, like I said, you can kind of go on forever. But one type of statistical model that people are often interested in is not just occupancy, not just whether a species was present, but how many there are, right? So it's hard. And that's almost all I'm going to say, and because there's a lot of people who have worked on stuff like this, and if you want to talk about it, we can talk about it. I can send you a bunch of papers. But like really the high level thing to know, like kind of along the lines of Dan Morris's talk when he said like, what do you tell someone who's interested in AI? Like if they say like, I want to know how many of something there are, it's kind of immediately a red flag. Like you need to kind of have this alarm bell saying like, that's a much harder problem than knowing whether something was present or absent. And there are probably exceptions, like maybe in satellite imagery, it's easier to count the number of zebras or whatever than it is to like count birds in audio. But in general, this is a hard problem. And the reason it's a hard problem is usually because it's hard to distinguish individuals, right? So if you want to distinguish individuals, go talk to Sarah.
Well, there's distinguished individuals or recognize them again over time. That's like so aerial bird surveys, counting an aerial bird surveys is actually not that hard of a problem. Count all the birds. Re-identifying the same one later in time is a very hard problem. Talk to Kyra. Look at this diagram at the back of it.
This is
it's so hard.
Yeah, so there's two pieces to it. One is whether you can just tell how many of something are in one sample, and the other is can you tell if the same individual reappears.
And counting how many there are in one sample, if you can see all of them, is different from counting how many there are in one sample if you can just hear all of them.
Yes, very different. Yeah, so if you're interested in this kind of thing, especially something to think about in acoustics is estimating abundance of unmarked individuals when you can't tell them apart. There's kind of 4 general approaches that I'm just putting out there in case you're interested, and the slides, are going to be online and stuff. And I'm happy to talk about them more. But yeah, the overall takeaway is abundance is hard. Okay, before we go to a couple of real-world examples, are there any questions we should do first? Perfect. Sweet. So I'm going to talk to 2 real-world examples from my lab from acoustics, and then Nadia's going to talk about one example or one project he's been working on for the last 15 minutes or so. So the idea here is let's look at real data and a real model that we trained and figure out what we can do with the model to answer the question. So in the first example, the question is what are the daily and seasonal activities of a frog's, or seasonal patterns of a frog's vocal activity? So we want to know, like, is a frog more active at night or during the day? Are there certain weeks of the year when the frog was most active, right? So we recorded audio. This is actually like underwater audio moth recorders in lakes in the mountains. And they're just recording like a 1 minute audio clip every 15 minutes, 6 weeks. So we get this kind of long time series data. And we trained a model, CNN, to detect the calls, and we trained it on a random subset of the actual field data. So this is kind of best case scenario where the training data and validation data are directly and randomly drawn from the application that we're using. So we can expect that at least on average, the performance of the model is going to look very similar to what we see in our validation set. And so our model this is actually the same histogram I was showing earlier, but this is the application of that model. It's pretty good if you want high precision and low recall, and it's bad if you want high recall and low precision. So what should we do? What would you do?
Threshold?
Pick a threshold. Yeah, so we can pick a threshold, and what threshold would you pick?
Maybe further down, I don't know.
I don't have numbers on here.
Like there, maybe?
You want to maximize recall.
Want to maximize recall. So if we maximized recall, it would be somewhere down here. We'd get a bunch of false positives.
Yeah.
And then would you review your clips to find out if there are false positives?
Yeah, I mean, I think if you want to do daily, like dial activity patterns, then you kind of need to see all of the frog calls, even if you're going to get some non-frog calls in there.
Are these like on a log scale or?
No, this is linear.
So it's somewhat balanced between.
Oh, yeah, actually, sorry, that's a caveat. This is a balanced validation set. The actual data
That
is
matters a lot, right?
Yeah, so the positives might be more rare than they're showing here. That's a good point.
Are you taking these data out and are going to put them in an occupancy model later? Is that like, are you?
So in this case, the only thing we want to do is like draw a graph that shows like what's the temporal activity pattern over the day and over the season. So yeah, the kind of key point here is that like if we want to do like daily activity pattern across the entire season, it becomes infeasible to review a lot of clips for every day in every 15-minute window, right? And so we want to be in a scenario where we don't have to review the clips. And so what we actually did is we picked a high threshold, and we picked the threshold high enough that we said we were pretty comfortable with the fact that the model is not going to have a lot of false positives, and that that temporal pattern would be the correct temporal pattern without even needing to review the positives. So
Sam, can I ask a question? Could you also have a scenario though, so that's a balanced validation set, where in the real world, maybe like your frogs are calling for 100th of the time. So if that's going to 100 times your ratio of false positives to true positives.
yes.
So if there's a little bit of error, or you'd be comfortable reviewing that smaller subset. Is that what
That's a good question. So like if this orange one got super big and the blue one got super small, and we have some threshold around here, right? We could actually be getting tons of false positives relative to our true positives. But if our threshold's way out here, then even if they both grow a lot, you still have high precision, right? And you just have low recall.
Yeah, so you're trying to eliminate all the false positives.
Yeah, and there's kind of a trick here as well, because when we decided that we wouldn't review all the positives because we wanted some like detailed temporal resolution that was, too much to manually review, we picked a really high threshold, but then we also picked a bunch of other thresholds, right? And we showed that if you just normalize for the total number of detections, the thing we were interested in, which is the temporal pattern, was the same across those thresholds. So even though we know the precision and recall were changing, and the total number of detections were changing, the ecological answer to our question was the same, which was that the frog was more active at night, even though we expected it to be active during the day. And so even without manually reviewing, we could show that, okay, in a scenario where we know we have really high precision, really high threshold, we get some pattern, and then we lower the threshold and we get the same pattern.
So if you go back one slide and you take that very high threshold, like on the right, where there's maybe like 3 orange class in there.
Oh, like here? Yeah.
Yeah. So if you pick that one, how do you know, like, are you missing something that has like a very strong pattern? Because you're rejecting
All these
the ones on the left, and I wonder whether all those detections have some form of pattern to them. Like, what if those are all the daily frogs?
Yeah.
And then you just rejected all the daily frogs, and now you plot your occupancy.
That's a great point. So that's an implicit assumption when we did this, is that there's like some there's not like structure in what's being detected or not, right? That you have like a lot of the statistical models, even though this isn't even a statistical model, have this assumption, which is about detection probability, right? So I said if there's unmodeled heterogeneity in detection probability, they're going to fail. So that's exactly what you were saying in different words. The detection probability is different for different subsets of your data. It's going to be different. But what's nice is that if we lower the threshold, we see the same pattern, right? And so the idea is that maybe now with a lower threshold, we have more false positives, but we also capture those maybe different part of that positive histogram. We see the same pattern.
Did you get at that unmodeled detection, just sussing it out by like looking at some of those ones that fell in that zone that Bjorn was talking about? Like being like, oh shit, these are all at like it's all rainy, or something was happening.
Yeah, exactly. So a great thing to do when you have a histogram that looks like this is just look at a subset of your data stratified by score. So why are some of my positives scoring low? Why are some of them scoring high? Yeah, get an intuition for that kind of thing. Cool. Let's look at one more example. In this case, we have a detector that's detecting a bird called the American woodcock, and we're going to run an occupancy model because we're interested in what habitat covariates are associated with this bird, which is a popular game bird. People are interested in the conservation and game management here. And they're interested in the habitat covariates that predict the occupancy of this bird. And we record audio every day across the breeding season. We have 100 points. And this is what our histogram looks like of a class balance validation set. So what should we do?
You need basically perfect precision unless you're going to review them later. So your threshold would need to not include any negatives.
Okay, so we can pick a really high threshold if we don't want to review anything. And then it could kind of come into the scenario Bjorn was talking about, right? Where if some of the ones that we're missing because of low recall are associated with certain habitat characteristics, but are also occupied, then we'd be kind of losing information in our occupancy model or misdirecting our occupancy model. So is there any other approach that we could take other than picking a really high threshold?
You could look at, if you take the ones that look like a super high threshold and say, okay, we're pretty sure that there's occupancy across these, and then look at the rest of them and see if you're consistently seeing predictions at certain locations and prioritize labeling there.
Cool. So another way of saying that same thing is that at sites where we don't have high scores, we might want to review some of the detections that we think might be possible.
Yeah, review more based on your end goal.
Based on the end goal. And the end goal is basically in an occupancy model, we're trying to detect it as many sites as possible, right? And once we get a detection for each kind of like window of our detection history, so maybe we have like 10 consecutive days of visits, but on any given like visit or day, we really just have to get one single detection of this bird, right? So we're gonna have like 5,000 like little audio clips, and each of them is gonna get a score. But if we just confirm that a single one of those has this like peent sound that the American woodcock makes, then we're done. We have the occupancy model saying the site is occupied for that day.
Could you make the same plot for each of the sites and then see where that threshold lies? Do you know what I mean? Where your purple things, are encroaching into the area. So you could.
Yeah, you could if you had labeled data for every single site, right? And enough labeled data to draw an intelligible histogram.
But what you could do is you can make a cool map where you put the highest confidence detection for each location.
Wow, good job.
Okay.
So what we did is we decided that all we need to do is try to detect it at each site, right? And so all we're going to do is go to each site and review just a handful, maybe 1 or 5 or 10 of the very most confident samples of the detector at that site at that day, right? And so like you can imagine if you have like 5,000 scores on some site and you just go review the top 5 scoring ones, like based on this histogram, like if the site is occupied, you're just going to hear the thing right away. You're going to find the thing you're looking for right away because you're just looking at the very most confident or highest scoring samples for that day in that time period, or that site in that time period. And you can repeat that across sites. And the key point, like Sarah pointed out, is that there may be a site, right, where all the scores are low, but you're still going to go and listen to just the 5 highest scoring samples. And maybe you'll be able to detect the thing that you were looking for, even though if you had picked some threshold that has high precision, you would have missed it because you're throwing out all the lower scoring piles.
So this gets actually kind of into the re-ID question, which is like, I mean, I guess here you're guaranteeing you don't have false positives, but there's still, of course, the possibility of false negatives.
Exactly.
And so, so assume you can take, out of your 100 or 500 sites, assume you can basically just really easily confirm a bunch of them. In the re-ID problem, this is like, the correct match. Like you're able to say, here are the top 5 matches, and you can see right away that it's clearly the top match or the second top match. So you're like able to get through those very fast. If you look at those top 5 for some location, like say there's like 2 locations, you look at the top 5 and you don't see anything, and you look at the top 10, you don't see anything. Like how far do you go to convince yourself that it's really not there? Or in the re-ID problem, to convince yourself it's truly a new individual.
Right, yeah, so the strategy we took here is actually like you do fixed effort per site. So you're always listening to a maximum of, for instance, 5 or 10 samples per site. And if you hear it in the first one, you can actually stop because all you need to know is that it was occupied. But if you don't hear it in the first 10, you stop. And so this is really relying on the ability of your occupancy model to handle imperfect detection, right? To handle low recall.
But what if there's biases that you're not capturing? Like what if like there's some sort of systematic like ecological bias in your model? So like you don't realize it, but you're systematically under predicting in a certain like environmental space.
I would argue you cannot fix that without labeling everything.
But maybe you only have to label everything at some sites, or you only have to label a lot of stuff. I think you can't fix that. I'm genuinely asking, like, how do you try to address that potential issue?
That's in the occupancy part of the model where you make that a function of stuff. Like you have this imperfect view through this process, but then you're making the true occupancy a function of different things.
You can try to model that.
My question is basically like, if we can guarantee that your model is somewhat like equally good across all your sites, then I think that is completely reasonable. But what if it turns out like some of your sites are a swamp and there's something else that like is confusing the model or whatever, and like
that's back to the unmodeled detection issue, right?
Yeah. So ideally, you come up with some detectability covariate that accounts
right
for the uneven detectability across.
And you try to calibrate that.
Actually, the occupancy model will learn that if you model it with a covariate that represents that.
When you're looking at the pictures and you're like, this is really swampy, I don't see anything, like you could write that could be like a swamp, and then you put that in the detection.
It comes down to whether you can measure the thing that's causing the heterogeneity. If you can't, then you can't.
Okay. Genuinely asking, guys.
Yeah.
Super interesting.
Yeah, no, that's important. So like if you can measure the thing that's causing a difference in detectability, your occupancy model can model and account for it. If you can't measure it, or if you don't know it's there, there's nothing you can do about it.
Mm-hmm. So is there a way that, I've been thinking about this from like a quality control perspective, like over time. So say you have a model and it's like, it was really good and now you're running it on the same sites over time. Like how do you recognize when changes in your predictions are actually because the environment is changing or because your model is changing? And so like, do you have like some sort of like random quality control that you do? Like how do you kind of try to capture model change versus ecological change?
I'm going to hand over Maddie now, but I'll do a brief answer, which is my short answer is like anytime you can get a random sample of the actual like new data that you're using your model on, that's a good way to get a sense of things have changed much. Cool. Or like annotate a random sample. Oh, yeah, I'm gonna hand it over now. He's gonna talk about a pretty cool project that he's been working on.
Hey everybody. This is a little bit of a departure from what we were previously talking about, but very much ties into what Justin presented on yesterday in terms of how to deploy your model, how to set it up in a system in which users can make predictions from it. And in this case, basically, this is sort of like the one area of this entire ML world that I have some experience with. And in essence, it's operationalizing machine learning models. So typically, what I mean by that is like, we all have these models now, or have like, you know, something that generates predictions, and we are able to invoke it on the command line and run our Pi, you know, test or predict scripts and everything like that. But what happens when your end user is not somebody who took this class, or not somebody who has experience, you know, whatever, chasing down dependency conflicts in Python, or whatever, comfortability with the command line. Or maybe they do have experience with that stuff, but they just don't have GPUs locally, and they want to be able to sort of like leverage all of the insights and benefits that your models hopefully, you know, produce. So what do you do in that case? And I think in a lot of instances, the answer is you build a software application that integrates the model into it, build a user interface for it, and make it accessible to sort of regular, you know, non-technical people. But maybe before I like sort of dive too deep into it, I'm kind of like, I assume that a lot of us in the room are ultimately going to be the end users of our models, and we're creating these models for ourselves to assist with modeling or whatever sort of downstream tasks you might have. You're going to be running locally. You're going to be running on some sort of, you know, GPU cluster or something like that. So this is like less applicable to that kind of people. Is that, maybe a show of hands, is that like everybody here? Or is there anybody who's like curious about integrating their tools into some software for some downstream? Okay, more than I thought. That's good. Yeah, so my sort of, let's see. So my sort of journey into this started a couple years ago. I work for the Nature Conservancy, which is an environmental nonprofit, and I am a software engineer. I'm not a machine learning person or an ecologist. But there was one day my boss came to me and he said, there's a preserve that we manage called Santa Cruz Island. And he said, the folks out there, they have these camera traps set up and they generate a ton of data, very difficult and time consuming to review the data. And they're trying to use the data to sort of inform whether or not they have had a invasive species incursion onto the island. So just the sheer like timeliness, the time-consuming nature of reviewing the data pretty much makes the whole effort sort of mute. So he said that they had kind of separately, totally on their own, had heard somewhere that machine learning could kind of help with this problem. They, I think they hired a company called Samasource to do a bunch of the labeling, and then they hired a contractor to train a classifier. They had this classifier, and they're essentially like in the situation that, like, I don't know, all of us are in now or might be in soon, in which we have a model, but they, as the ultimate end user, like didn't have a really good, efficient, or clean way to kind of draw information from it to make predictions. And as we all know, like, who can blame them? It's a friggin' pain in the ass to set these things up and get them running on GPUs and extract predictions out of them. So I think basically the core problem that software in this situation hopes to solve is that machine learning models are beyond not user friendly. You know, they're like user hostile. They're the worst possible you know, product you could wind up with to put in the user's hand. So that's where I think this has value. Okay, talk about that. End user. Okay, so I'm going to talk about, so the origin story has very much to do with Santa Cruz Island. for those of you who are like genuinely interested in building out or deploying their models to the cloud, building an API around it, integrated into a cloud-based application or mobile app or anything like that, I am so more than happy to talk with all of you about like technical approaches to doing that and considerations. What I'm going to touch on right now in the next couple of minutes is more just like high-level considerations from the perspective of a software developer. And ways to sort of start thinking about your problem and centering your users at the, sort of at the focal point, or giving them the importance that they deserve in your whole system. So that's just, any sort of software project should start with a good sort of definition of the requirements. For us, we had this custom model, and we needed to make inference requests to it. We also had a need to consume images from sort of your traditional SD card-based cameras, Reconnexes, et cetera. So that would be what Justin was referring to yesterday as like batches. That's kind of one distinct need from real-time inference, which we also need to support because we were hoping to move into this wireless camera trap space in which we're getting fed this drip of images, and we wanted to perform inference on them, and then ultimately send alerts if something of concern was detected. And then sort of going into it wide-eyed and knowing that like our model is not going to be 100% precise, we needed to be able to sort of review both the images and the predictions remotely if one of those alerts got triggered. And ultimately, like, hopefully go back and with some degree of cadence and review all the images that maybe didn't trigger an alert just to make sure there wasn't any misses. So like when I was first getting into this was probably like 2020 or something. I was so sure there must be like some software product out there that would kind of meet those requirements. And I looked and looked and looked, and like there are a ton of applications that are like designed for camera trap data management. Many of them check like 2 or 3 of those boxes, but I couldn't find anything that kind of was doing everything we wanted to do. So I kind of like rolled my own, and that's how I got into this. Some of the core like design principles I wanted to make sure came through in the final product was this ability to kind of like easily deploy and then integrate your own models and potentially open source models like Megadetector or other models that other people have developed that are out there into your work streams, develop, sequence them in your own custom pipelines. And I guess that's sort of like a bit of a departure. This was one thing that I was very surprised that other applications weren't doing that I found. There was a lot of applications at the time, there still are, that sort of take this paradigm of like a Wildlife Insights, for example, where they are building an application around a backbone of like a single sort of like general purpose classifier, general purpose model. Wildlife Insights, for example, is attempts to sort of provide predictions on all kinds of species from all over the world.
It's been like an active like discussion or like priority that just hasn't been able to be prioritized with the capacity that the Wildlife Insights team has to like support custom models.
Oh, really?
I think eventually that will happen. It's just, yeah, it's one of these things where it's like, do you support a new continent or do you like refactor so you can people put their own models in, and it hasn't yet been like something that they got to be able to.
Cool, that's cool. I think the general, my takeaway is there's a need for both, you know what I mean? Like the Wildlife Insights classifier is gonna work really well for a ton of people. If they're trying to detect, whatever, the most common species are detecting common traps.
Common species in East Africa,
right.
California.
Sure. But as we all know, yeah, as we all know, we're all sort of designing super sort of niche specific models for our own specific needs. Like there should be an easier way to just basically operationalize them, pull them into a production camera trap image review workflow or data review workflow. The second part that I saw that was kind of, I felt was missing from the landscape was that there wasn't, again, this has probably changed since then, it's been a bunch of years, but at the time there wasn't any application that sort of treated the human labor component of it. Like if you presume that somebody eventually will be reviewing the predictions that your model generates via some user interface, and if they have an opportunity to validate or invalidate them, or draw a bounding box around something that was missed, maybe for their own purposes, for the purposes of exporting the data to some downstream modeling task, or for the purpose of just creating a structured data set. Like nothing was like capturing that in a way in which it would, you could export it specifically for like model training purposes. And then with those sort of new iterations of the models, allow for the easy sort of redeploying of them. And basically there's this term, humans in the loop, which in which you sort of like treat your model as this like living thing, that like an iterative thing, rather, that it's making predictions, humans are correcting or amending those predictions. That feeds back into a training cycle, and then the machine learning model improves. So that was another core principle that I wanted to kind of like carry through. I didn't see other people doing. And we are almost at time. I'd love to do a quick demo after this, but I'm just going to touch on one more slide here of just like sort of high level software consideration things. Is like, kind of like, you can kind of frame a lot of stuff through the lens of abstraction, or on this like continuum of how abstract a solution is to a problem. But I find it really useful to think about software design decisions. In fact, I think you can think about every piece of software design decision along this spectrum thing. So if you think of a super general purpose piece of software, like on that far right end, like an extreme example would be like a Linux operating system. That is a very, very general purpose piece of software. Because it's general purpose, it's useful for a ton of people. It's a huge potential user base. As you move sort of to the left, as things become more task specific, that potential user base is obviously becomes a more niche thing, a more niche problem. Fewer people have that problem. User base, potential addressable user base, the aperture kind of closes a little bit. So there is, and then the other thing I put here is like, when you're about to start software, any kind of project, like there's a, and you're trying to assess like, is this worth my time? Like, is there a high enough ROI in terms of conservation impact, based on the number of hours I'm going to put into this thing? Like you are going to want to push yourself towards a more general purpose solution, because you want it to be useful for the most amount of people and the most amount of use cases and the most diversity of data types, et cetera, et cetera. Because otherwise it might not make a ton of sense. Like for example, the software that I ended up building, if I had decided to build it specifically for Santa Cruz Island to meet their needs and just hard code in their single model that we had at the time, probably wouldn't have been worth my time. It would have been 10 people using it. It would have been way more efficient for me to just go and label all their data for them by hand. Like way more efficient. So there's a healthy push towards or tug towards general purpose, a more abstract software design, which I think is good. However, there's a couple sort of like things in tension and costs of doing that. One is that I put user experience here. It's more like an efficiency thing. One is just that like, if you are doing something super task specific, you can take advantage of all the nuances and domain specific characteristics of that task in your UX design and make that user experience like way, way more efficient. I'll give you some examples in a second, but versus like if you're Linux on the other end of the system, like it's whatever you're trying to do, I'm sure you can figure it out or do it, but it's not going to be as efficient as somebody who built like a very specific task, specific app. The other thing, cannot say this enough, from like an engineering perspective, the higher the abstraction, the greater the cost, the more complexity, the more time consuming it is to implement. It's just harder to anticipate the needs that more people might have and design for them. So that's a huge consideration. Yeah.
So I think another thing here, like a sort of like region or failure mode that I feel like I've seen somewhat consistently is software developers anticipating that there is a general purpose audience for their tool and anticipating what that general purpose audience's needs might be without really actually having like a direct set of users that they're already engaging with that are representing those different needs. And so then designing something that they try to make very general at the cost of actually building something anyone can use.
Yeah.
I think if you think you have a general purpose audience, like go find them, make sure you have like sort of, if you think, oh, well, someone might want to use it this way and someone might want to use it this way, find two people that want to use it that way that you think they might, and then have them beta test it for you. Like make sure that you're not hallucinating users.
That's such a good point. And just to, one thought on that is that, because typically what you start it with is the specific, somebody came to you with the problem. You know the target audience for the task specific thing, but you are sort of just imagining, well, other people must have this problem. You don't really know unless you go out and find them.
And don't spend a bunch of cost and complexity on building something that then ends up actually not being useful for your actual user that came to you with their problem.
Yeah, right.
Or being less useful for them.
Right, because again, you're going down on that efficiency scale as you move forward. Yeah, Justin.
Yeah, I was just gonna say, I feel like another way of describing this line that's going down is like the usefulness for each individual user of your thing. Like if you build it for one person, it does everything that they want. If you build it for everybody, it does like a tiny fraction of what they want.
Yeah. 100%.
And you will have infinite feature creep.
Yeah. So sort of related to all this, I'm not going to get into it, but it's worth reading the Wikipedia page on, or just having an idea going into any sort of software thing. It's like, we heard the concept of like lean development or lean methodologies, Toyota thing. Start with like a minimum viable product, bring that to find your users you think are going to use it, have them actually use it, provide feedback, make it. That's the high level thing. But okay, sorry, we're over time. But the just to like, I guess give some for instances here in the camera trapping space. So like, I guess wildlife insights would be like, we're talking about camera trapping, so this is obviously a narrow band of the whole thing to begin with, but wildlife insights is designed to be pretty general purpose, and so it's going to have a large addressable user base, but because it might not be super accurate for your rare species, it's going to be more time consuming for you to ultimately end up with like a viable labeled data set. There's this is something I've seen a lot with like other camera trapping applications, but there is a tendency to be too task specific in my opinion. So for example, like Trap Tagger, for example, which is like a really, I have a ton of admiration for, a cool product. It was designed for I think originally for one group out of Oxford, whose name I can't remember. Do you know what?
Their initial models were for South Africa.
Okay.
They were working with a group out of Oxford that was studying South Africa.
Okay.
And they basically designed something that worked really well for South Africa, and then they sort of have slowly been expanding the set of areas they support.
It's not even that the model side of things that caught my eye with this. It was like, the developer, so the group that was setting up the camera trap surveys set the cameras up in a pretty specific way in which they had two cameras facing like a target location, trail or something. And so typically when it was to increase detection probability, but typically if a lion or whatever comes and walks by, you have a cluster of images that are both temporally and spatially sort of grouped together. So the sort of observation, smart one, that the developers made was like, instead of having the users review every single one of those images, let's group them in time and space and surface like, the highest probability or highest confidence detection there, have them label one, and then just like apply that to all the other animals. Now, that is going to work for a lot of people. It wouldn't work for us, in which we can't just assume that because for starters, maybe people don't have location data, so that's one thing. But then, we in our use case, we couldn't just assume that two cameras firing around the same time in the same place are the same animal or species.
Cool.
Yeah. Okay. I guess I'll do 2 seconds, just like show you the thing to because just bear with me. No, I can do this. So this is can be kind of cool sometimes. So a lot of this data is coming from like the wireless cameras. So we might see some data that's like fresh and might be interesting. Although, oh no, it looks like somebody's been in there reviewing stuff. But really quick, I'll just show you how like the sort of custom model integration and pipeline part works.
But these are like images that were taken like 6 minutes ago. So cool.
Yeah. Although I don't know, a computer said I can't the mouse.
I think sometimes the projector screen makes my computer laggy.
Oh yeah, okay, whoopsies. What? Yeah, so I don't know. Let's see if there's something interesting going on here. Yeah, little proboscis deer mouse. In this case, we have an animal prediction and a rodent prediction. That's because for Santa Cruz Island, we're doing, mega detector is doing a first pass. If an animal is detected, we then do the pass through our classifier. So it provides an interface for basically, validating those labels. It's not perfect, obviously. Here it's thinking this mouse butt is a rat. But here's Sarah actually helped us set some of these cameras up out on Danger.
Oh yeah.
So this is a different location, but we can maybe see what's coming. Okay.
Yeah, friendly recommendation. Invite your neighborhood computer scientists to go set up cameras with you, and they'll get really excited about your data.
So people walking around earlier.
So they're doing the labeling in this thing you're showing us here, right? Like this is the interface where.
They're reviewing, right?
Yeah, so like if there's like a little perforated ring around the label, it's just been predicted by a model. It hasn't been validated yet. But yeah, you can get in there.
It's a sweet interface. And then you can you validate that. That's kind of a nice little interface that you have to go validate it. You had a check mark and an X, and you can also rename it.
Yeah, and add another object if there's not one.
Really nice.
Natty is really good software engineer.
Can we use this without it?
Okay, and so the very last thing I would look at this little herd of pigs coming in from last night. God, they're huge. Sometimes they come and knock over the cameras.
So the big white ones are labeled as empty, right? Stuff's just hard.
Yeah. Sometimes mega detector gets them, sometimes not. But real quick, so like for how the automation side of things works. I'll go back to this. It's sort of the way I rigged this up is sort of like you think about it like Outlook rules for redirecting emails from certain people to certain folders, but so it's like an event-based system. So in our case, we have a rule that says detect objects. Anytime an image gets added, request inference from mega detector v5a. Another kind of handy thing is you can adjust the confidence thresholds on a per class basis, or just turn some off entirely if they're not relevant. Like we don't expect to see vehicles here. It's an island where there's very few. We don't have to go around removing them from the labeled data set. The secondary kind of trigger model that gets run is this Mira is our Santa Cruz Island specific classifier. So when a label gets added that is an animal, presumably from the mega detector model, run inference. And then the same way is how you configure kind of these alerts. When a rodent is predicted, send an email. So the last thoughts on all that for those of you who are in this boat where like you want to make your model accessible to people, like I sort of like went out on a limb and did what Sarah said you shouldn't entirely do, which is like I made this assumption that there are other people in my camp that had classifiers they wanted to deploy, users who didn't know how to invoke them locally. And so we were starting to sort of expand our user base. We're working with other organizations in Hawaii and Bermuda and New Zealand and helping them integrate their models into their own work streams. But if any of you are interested, come find me. I'd love to talk about getting your models on this and talk about how you might use it. Alternatively, if you want to sort of look at the code and take pieces of it, it's all open source. There's a slide here with links to the repos. And yeah, happy to share what I know about it. But yeah, thanks.
Yeah, hey, thanks. That's awesome to see that. It looks really, really cool. And I'm interested in, like, I've got an audio detector. I'm interested in, like, sharing open source so people can use it. It's not something I've ever done before in terms of, like, operationalizing it. And I've heard you can have real headaches with, like, versions and operating systems and things like that. That means there needs to be, like, maintenance over time. So yeah, how labor intensive, say, like, I would be going for something that's very, like, task specific rather than general. How much labor do you find that maintenance takes? You know, like versions update and things like that start throwing errors.
It's like the bane of my whole existence. I mean, it's a huge deal, and it's the biggest, it's the biggest gap in like the sort of software for conservation space in my mind. There's no funding for doing maintenance. A lot of these tools don't generate revenue, so there's no incentive to improve them or keep them running, and so you get this sort of like lurchy development landscape where people build something because it's new and cool and can do these things, and there's excitement around it, and then that excitement dies off and the maintenance does with it. It's really important, and it's time consuming, and it's difficult to assess at the outset how much time it will take. It's going to be highly dependent on like your stack and what kind of software you're building.
Yeah, are there any like approaches you like selecting like stack of what you're using then? Say if you want to go really task specific, is there any routes you can pick that will make it easier for you that you're aware of?
From like a maintenance perspective?
Yeah, for operationalizing it, say you've got your trained model and you've got a bit of Python code that pre-processes data and then processes output from the model, like puts it in a nice spreadsheet or something. What's like the easiest thing you can do to just get that's something that, you know, a lay person can get working on their laptop or something?
So something like that I would recommend, and it would be pretty stable in terms of maintenance. I would recommend deploying it to a cloud service as like a invocable endpoint like AWS, Google Cloud. And I can set you up with scripts for doing that on AWS.
Cool.
And I don't know about Google Cloud, but AWS at least has pretty nice like endpoint types that are scaled to 0, which means that like when it's not being invoked and it's not being used, you don't have to pay for a single thing. It's like an on-demand service. That makes something like this cost-effective because you're not paying for it all the time, only when it's being used. And if you build like a sort of simple API around it, then yeah, I guess people could call it from their command line, or you could figure out like a simple desktop-based GUI that would just like send a request to the API maybe, or like little website that sends a request and downloads a CSV or whatever, you know.
I was going to say one last question on that. So I know some of my potential users like have terrible bandwidth.
Yeah.
And it is data.
Bring up.
Yes. That's a real deal breaker about cloud-based computer stuff. I mean, it's like
when you're talking about your end users and like all the potential end users, like there's now a Wildlife Insights desktop client, and different people have built desktop clients around Megadetector for this exact reason, because this is like a fundamental issue. And actually there's a pretty consistent set of people worldwide who have like a very specific workflow, which is like they run Megadetector locally to decide what images to upload on their limited bandwidth to Wildlife Insights to get classification. So now if Megadetector misses something, you're just SOL, but it still like makes that more feasible. But people have very different choices that they make. With Megadetector, we were just like, okay, we're gonna like provide the weights to the model. We're gonna have a repo. We're gonna provide a lot of tools to like help people understand how they might use it. And because it was such a useful tool, then community members built infrastructure to, for example, run it on a desktop, but I didn't build that. And then since they want to use it and run it on a desktop, they are maintaining it. That only works if it's a model that ends up really saving a lot of people a lot of time.
Yeah.
And so if it's very task specific, you're not going to have that trade-off of like, oh, a community is going to build around this and like make the infrastructure they need to cover these different types of use cases. But bandwidth, if bandwidth is a limitation, I honestly feel like you might need to just focus on one or the other. Address the not bandwidth limited group, make it work for them first, or address the bandwidth limited group, make it work for them, and then dealing with different people wanting to run a model on different like laptops and stuff that's where it just gets really nasty.
Yeah, for sure. That's a huge advantage of cloud-based software is that it's a more standardized compute environment, which is being invoked.
Yeah. Thanks.
Yeah. First off, this is super cool, and I think an idea that could be really useful to a lot of people. Say if I wanted to use my machine learning model with this sort of user interface that you built, is there any sort of like standardization to that model that I have to sort of do, where say that it requires standardized input or output, or I guess like how flexible is something like Animal to I guess just different types or structures or architectures of the model?
We would have to play around with it a little bit. I mean, it's sort of like designed in like a microservice architecture. So like the different components of it should sort of stand on their own, and they should provide like their own self-defined kind of inputs and outputs interface. And then, so in concept, you should be able to deploy any type of model for one of these endpoints, and then build your own pre-processing scripts and provide, figure out what the shape of your payloads and response, whatever it's going to be. It is one of the design decisions we made is that it's designed for camera trapped images. So I haven't really played around with like if in your use case for example, like skulls, or like I haven't like uploaded regular images.
Yeah, just like like if it wasn't, it sounds like it's mostly being used right now for like object detection kind of stuff from camera trap data. Whereas if it was just like I just want to classify this image.
That said, in theory, it would work. I wouldn't be that surprised. If it worked just fine.
I'm guessing that the bigger challenge wouldn't be once I have the images somewhere that they're accessible by this thing, like choosing what to run them through. I actually think probably like depending on the scale of your data, a much more complicated thing is how do you get your data to where the models live?
Yeah.
Like if it's like now you need batch upload because you have like huge amounts of data, or like what metadata do you need to like keep with that, and like how is that maintained? Like there's that stuff will end up being more custom probably.
Yep.
And right now you have a really cool thing where you've set it up so it's like direct online images being sent.
Yeah, yes. We're about to release like our sort of batch upload functionality, which you can upload like 50 gigs at once, and it'll spin up a bunch of sort of cloud-based compute.
So if you have to do more than 50 gigs at once, you just sort of run in 50 gigs, wait, get results, swap it out? Or?
No, you could, it's all concurrent. So you could, if you had more than 50 gigs, you would break it up into different 50 gig zip files, and then you could fire each one off. That's like the max you can have.
And then if you're bandwidth limited and then the zip file is like breaks, like the upload thing,
that's tough, yeah. Yeah, we should probably get that. Okay,
yeah.
Cool. Anyways, thanks a lot. Yeah. Thanks, Danny. Black chair, I guess.